Perfect. Can you see my screen?
Yes.
Okay, good. Okay, hello everyone, and welcome to this talk. My name is Obada, and I'm going to talk about the coexistence of quantum and classical channels over hollow core nested anti-resonance knotless fiber. So the vision behind this work is the quest for a reliable, seamless coexistence medium in which we can coexist the quantum channels with a high-power classical channels without having a major effect on the quantum channel performance. Usually, the quantum channels are used to distribute the quantum states, such as phase-encoded photons or polarization-encoded photons, whereas the classical channels are used to exchange measured information about these states. So far, the coexistence of both quantum and classical channels is a single fiber has been implemented using single-mode fiber. However, single-mode fiber limits the coexistence due to two factors. The first and major factor is the nonlinear effects such as Raman scattering and four-wave mixing. Because the power of the quantum channel is extremely low, around minus 90 dBms, and the power of the classical channels is order of magnitudes higher, the nonlinear effects really affect the quantum channel performance. And the second major factor is the loss of the single-mode fiber that has been limited to 0.20 dBs per kilometer for over 40 years now. We believe hollow core fiber can be considered as the ultimate medium for coexistence because it provides ultra-low nonlinear effects with ultra chromatic dispersion because the light travels in a hollow core, so there are no nonlinear effects. But also, it has the potential of having a much lower loss than the single-mode fiber. In fact, more than 10 times lower than the single-mode fiber. This slide shows the process of improvement of the hollow core fiber in the previous 5 to 7 years. As you can see here on the left part of the slides, the losses has been improved from around 200 dBs per kilometer back in 2015 up to the 0.28 dBs per kilometer, which was achieved by the Optoelectronic Research Center at the University of Southampton. We're going to mainly focus on these three red dots here. So this was the first anti-resonant knotless fiber that was fabricated by the University of Southampton, and it had the loss of 1.65 dBs per kilometer, and this is the fiber that I used for my experiment. The difference between the fiber here in ORC 2018 and the ORC 2019 is, as you can see, these membranes are thinner. And when you have a thinner membrane, you can improve the leakage loss and you can improve the reinforcement loss of the fiber. And as you can see, the loss went down. Here, they improved the geometry of the membranes. As you can see, the gaps between the membranes are almost identical. And the size of the membrane are also identical, which also helped further improve the losses. As you can see on the top right side, the losses could practically achieve levels that are 10 times lower than the single-mode fiber if we ignore the bend loss. By increasing the core size and improving the geometry of the fiber, we would hopefully reach a level that is 10 times lower than the single-mode fiber. On the bottom right corner, here I'm showing the recent fiber that was designed and fabricated by the University of Southampton. This fiber had a loss of 0.22 dBs per kilometer at the edge of the, in the C band, and at the edge of the L band, it had a very low loss of 0.20 dBs, which is exactly similar to single-mode fiber. So in terms of loss, we're reaching there. This is the experimental setup that I used to coexist 8 classical channels with 1 quantum channel in single mode and hollow core fiber and compare the performance of both of them. We have 2 bandwidth variable transposer transmitting 4 classical channels each, in which these channels are multiplexed using a wavelength selective switch that can act as a multiplexer and a filter. After that, the classical channels are further filtered with a sharp edge filter. These 2 filtering stages are required to suppress the noise level and provide enough isolation for the classical channels. After that, the quantum channel is coexisted with 0 dBm coexistence power when using the hollow core fiber. And the black line here shows the coexistence, either going through hollow core or single mode fiber. After that, we demultiplex both the quantum and the classical channels. The quantum channel then travels to BOB, whereas the classical channel goes to an optical isolator, which prevents the noise coming from the ETFA and from the local oscillators here at the receiver from traveling back to altering the quantum signal, we amplify the signal, and then we split it back to 8 different channels. And these are the results. As you can see here, when we coexist 8 classical channels with -9 dBm per channel, totaling 0 dBm coexistence power, we see a very minimal effect when we use the hollow core fiber. However, when we're using the single mode fiber, you can see that by increasing the number of channels or by increasing the power, we can see an 87.5% drop when using a power that is 40 times lower than the power using in hollow core fiber. So as you can see, the advantages of using hollow core fiber is clear, and we showed this in experimental. The Q-bar follows the same trend. As you can see, even when we coexist a lot of channels, 8 channels with a high power, we still have almost similar Q-bar. However, in the single mode fiber, the quantum bit error rate goes up, which basically reduces the secret key rate. That's all from my side. Thank you for listening, and I'm happy to take any questions now and in the remote sessions after this session.
All right. For some reason, I'm unable to start the video. Okay.
You are now.
Thank you very much, Obada, for this nice presentation. Since I don't see any questions on the Q&A, I can ask you a couple of questions. So how you told us about the losses and the fact that they are constantly improving. Can you comment on the losses for coupling in and out for the hollow core fibers?
So yeah, that's a good question. Thank you. The fiber we have in the lab had a coupling losses of 1.5 dB for each side, which is obviously a lot. However, the University of Southampton showed experimentally that they can push down the loss of the coupling in and out from the hollow core to the single mode fiber to 0.18 dBs per end, and the theoretical limit is 0.12 dBs. So they are reaching the theoretical limit of around 0.12 dBs for coupling in and out per end.
I see. And do you think that we can consider these fibers to be a realistic potential for the near future in terms of large-scale deployment? Or let me rephrase this. Where do you think are the main potential applications for such fibers?
This is still an active area of research. We have demonstrated the fiber use in quantum key distributions protocol. The University UCL have demonstrated this also in normal classical infrastructure. And I believe BT had a field trial using a field deployed fiber. So I believe since it's still fairly new, we can see this in quantum computing, quantum key distribution, and maybe in the edge part of the network where very low latency is required, such as 5G.
I see. And one last question coming from the audience. In your configuration, do you apply any quantum mechanics protocols? So
we applied the coherent one-way protocol. So we use the Clavis 3 system that uses coherent one-way protocol, if that answers your question.
All right. Okay. Thank you very much. If you have further questions, please, you can meet Obada afterward in the Remo section.
Thank you, everyone.